3 earthquakes in less than 24 hours on a fault that sits directly beneath one of Pacific Gas and Electric's oldest dams. Largest was felt 200 miles away from ground that barely anyone monitors. And what happened on Wednesday just told us something seismologists have been arguing about for a decade, but the answer is not reassuring. On July 9th, just after 5 in the evening, the ground moved northwest of Cavalo in Mendocino County. The United States Geological Survey recorded a magnitude 4, 0 at a depth of about 5 miles. That alone would not have made news. Northern California produces earthquakes that size routinely, and this one struck in terrain so remote that almost nobody noticed. But 59 seconds later, the ground moved again in the exact same location. This time it was bigger, a magnitude 4, 1 at nearly the same depth. And then at 3:20 in the afternoon the next day, Wednesday, it happened again. A magnitude 4, 5, the strongest of the sequence, struck roughly 19 miles northwest of Cavalo at just 2, 8 miles deep. That shallow depth matters enormously. That depth concentrates the energy near the surface instead of spreading it through miles of rock on the way up. It also means the same fault geometry applied to a much larger earthquake would be far more destructive than its size alone would suggest. A magnitude 4. 5 does not normally travel 200 miles. This one did because it was extraordinarily shallow. The earthquakes occurred in mountains east of Island Mountain, where 3 county lines converge on ground that is almost entirely national forest and private timberland. Nobody was hurt and nothing was damaged. The remoteness of that location is precisely why this matters. This fault runs through terrain where you cannot put instruments. The epicenter sits in the one section that the newest and best science on this fault does not cover. Scott Dam rises on 130 feet above Lake Pillsbury, roughly 20 miles south of where these earthquakes struck. Behind that dam sits 167 acre-feet of water. The dam and its twin downriver, Cape Horn Dam, comprise the Potter Valley Hydroelectric Project, a century-old facility built directly above this fault system. When some research models suggest this fault can produce a magnitude 7 earthquake with nearly 19 feet of horizontal ground displacement, you can understand why a concrete structure holding back that much water needs to know what it is sitting on top of. This is not a theoretical concern. This is not speculation. This is infrastructure protection that started decades ago. In 1986, and again in 1991, researchers named Taylor and Swan excavated across the Bartlett Springs Fault and read the geological layers. What they found has defined the hazard picture ever since. They found evidence of at least 3 prehistoric earthquakes, the most recent of them somewhere between 300 and 1,000 years ago. To be seen in a trench, a rupture usually needs to be larger than magnitude 7. A paleoseismic trench records surface rupture, the moment when a fault breaks all the way through the ground and offsets the soil layers. Earthquakes that never reach the surface leave nothing behind to dig up. 3 events in a trench most plausibly means 3 earthquakes at or above magnitude 7 on this fault. The most recent landing somewhere between roughly the year 1026 and the year 1726. That resolves an apparent paradox, and the distinction is worth being careful about. This fault has produced large earthquakes. It simply has not produced one during the roughly 175 years California has been writing things down. Hasn't broken in recorded history is accurate. Has never broken is false. The gap between those 2 statements is the entire hazard. The Bartlett Springs Fault Zone is the easternmost active branch of the San Andreas system north of San Francisco Bay. The San Andreas itself runs along the coast. The Macama Fault Zone runs in the middle. The Bartlett Springs runs farthest inland, carrying a share of the Pacific Plate's northwest motion that the San Andreas does not. It is by a wide margin the least studied of the 3, and there is no earthquake in the written record that can confidently be pinned on it. Physically, it is a right lateral strike-slip fault, meaning the 2 sides slide past each other horizontally. Its published length depends entirely on which strands you count. 170 kilometers in one assessment, 120 in the most detailed recent study, 85 in one national hazard model. Those are not small differences. The geometry is not self-contained either. The active trace runs southeast from north of Round Valley down to the eastern side of Clear Lake, where it steps right by about 2.5 kilometers onto the Hunting Creek Fault. Southeast of that is the Berryessa Fault, generally considered the northern end of the Green Valley Fault. Follow that chain far enough, and you're in the eastern San Francisco Bay Area. This is not an isolated fault in the woods. It is the northern end of a continuous line of structures running down into one of the most populated regions in the country. But here is the fundamental problem. 2 respected research groups have built 2 models of how this fault behaves below the surface, and they disagree. Not slightly. Fundamentally. Because they disagree, they produce 2 completely different worst-case earthquakes. The first model from Lozos and colleagues in 2015 says the fault is locked from the surface down to 10 or 11 kilometers. Locked means stuck. The two sides are not sliding, strain is accumulating, and eventually all of that stored motion has to come out at once. When Lozos ran the numbers on that geometry, they got a maximum magnitude of 7 to 7, 2 with horizontal slip of 5, 6 to 5. 8 meters. A fault moving nearly 19 feet sideways in a single event. The second model from Murray and colleagues says something almost opposite. The fault is creeping everywhere below 5 kilometers. A creeping fault slides continuously and quietly, releasing its motion a fraction of a millimeter at a time, instead of storing it for one violent afternoon. If most of the fault is creeping, there's far less energy available, and the maximum event drops to a magnitude 6. 5 to 6. 7, with about 6 meters of slip. Consider what separates those answers. A magnitude 7, 2, releases roughly 11 times the radiated energy of a magnitude 6. 5, and produces about 3.5 times as much slip. 1 is a serious regional earthquake that damages towns across the coast ranges. The other is a generational disaster for the interior of Northern California. The entire difference comes down to one question. How much of this fault is greased, and how far down does the grease go? The grease is literally grease. It is serpentinite, a metamorphosed ultramafic rock, greenish and waxy and mechanically weak. Laboratory work has shown that where serpentinite meets ordinary crust rocks, chemical reactions along that contact significantly reduce friction and stabilize the sliding. In plain terms, serpentinite is nature's grease. Where you find it in a fault, you tend to find creep instead of earthquakes. Until recently, there was no good way to answer this question because the fault runs through terrain where you simply cannot put instruments. In 2024, a team led by Victoria Langenheim published a study in the journal Geosphere that attacked the problem from a different direction. If you cannot measure whether the fault is sliding, measure what the fault is made of, and work out from the rock itself where it has to be slippery. Serpentinite has one crucial property that makes this approach possible. It is strongly magnetic. Even if you cannot walk into the terrain, you can fly over it and map the rock from the air. So that is what they did. The team modeled aeromagnetic and gravity anomalies along 14 cross-sections spanning 120 kilometers of the fault zone, folding in more than 5,800 gravity measurements. The work was funded by the Geological Survey and by Pacific Gas and Electric, which will matter a great deal later in the story. What they found on 13 of the 14 profiles was more serpentinite at depth than the surface geology predicted. There is more grease down there than anyone assumed. And if serpentinite predicts creep, then much of the Bartlett Springs Fault is creeping, particularly along the central and southern sections, where the modeled serpentinite extends 10 kilometers below the surface or further. The study came down on the side of the Murray model. More creep, lower maximum magnitude. In the author's own careful language, the results suggest a possible reduction in the maximum amount of slip from a single earthquake rupture on the fault zone. If you stopped reading there, you would close the paper feeling better about this fault than when you opened it. Almost nobody stops reading there, and the last two findings are the reason. The first is that the pattern breaks at the north end of the fault. The study's own words are worth quoting precisely because the precision is the point. The northernmost two profiles, they wrote, suggest that the serpentinite is restricted to the upper 1 kilometer or mostly southwest of the fault zone, in contrast to the rest of the models. Read that again with the mechanics in mind. Everywhere else along the fault, the grease extends far below the surface and the fault can slide. At the northern end, either it is confined to the top kilometer, leaving everything underneath ungreased, or it sits off to the side of the fault entirely, where it does no good at all. The argument for a lower maximum magnitude is an argument about the central and southern sections. The northern end does not appear to qualify. The second finding is one sentence long, and it is stated flatly. We do not extend our analysis north of Round Valley. That is the edge of the map. The best modern characterization of this fault's slipperiness has a hard northern boundary, and beyond it, nobody has done the work. Now, put the earthquakes back on that map. Kovlo sits in Round Valley. The events of Tuesday and Wednesday struck roughly 19 miles northwest of Kovlo, at or beyond the northern limit of the study area in the one section of the fault where the serpentinite model does not predict pervasive creep. This is why the sequence matters more than 3 moderate earthquakes in an empty forest should. The reassuring conclusion about this fault, greasier than we thought, less dangerous than we feared, was drawn from profiles 3 through 14. The ground that just moved 3 times in a day is not covered by it. It is in the gap. Gaps of this kind have specific mechanical significance. If the northern section is locked while the central and southern sections creep, the fault has a boundary inside it, a place where sliding rock meets stuck rock. On strike-slip faults, those boundaries are exactly where ruptures tend to nucleate and exactly where they tend to stop. There is a geometric complication right there, too. The Geosphere team documented that, at Round Valley, the old right-stepping geometry appears to have been abandoned with the active trace now making a left compressional step as it enters the basin. A compressional step is an obstacle, a place where the fault has to squeeze rather than slide, and obstacles concentrate stress. The earthquakes happened at the north end of exactly that structure. There is a counter-argument, and it deserves a fair hearing because it comes from the same study. Creeping faults are not silent. They produce small earthquakes routinely, and the accepted explanation is that a fault which is mostly sliding still contains small stuck patches. Knots of stronger rock embedded in the weak material. Those knots resist until they fail, and when they fail, they produce an earthquake. The geosphere team even found a correlation between where they modeled serpentinite and where microearthquakes occur. And they did not use seismicity to build the models, so that correlation is independent evidence. Small earthquakes on this fault are therefore expected. They are the signature of a creeping fault working normally. The problem is the size. That framework predicts earthquakes below magnitude 3. What happened on Tuesday and Wednesday was a 4, 0, a 4, 1, and a 4, 5. That is 1 to 1.5 magnitude units above the expected signature. And because the scale is logarithmic, the gap is larger than it sounds, somewhere between 30 and 200 times more radiated energy per event than a magnitude 3 would produce. That does not make these earthquakes anomalous in any absolute sense. Moderate earthquakes happen on all kinds of faults, and nothing here breaks physics. What it means is narrower. These events sit above the size range that the creeping fault explanation comfortably absorbs as background noise. The shape of the sequence points the same way. In a standard main shock and aftershock sequence, the biggest event comes first, and everything afterward decays in size. This did the opposite. A 4-0, then a 4. 1, then a 4. 5 with the largest event last. That is a swarm. And swarms are typically driven by something other than one patch releasing stress, usually fluid moving through rock or slow slip, loading a series of small patches one after another. Swarms are not new on this fault system, but the size of these ones is, and one detail resists tidy explanation. The second earthquake was both larger and shallower than the first. It stepped up toward the surface and got stronger 59 seconds later. This progression does not fit easily into standard earthquake models. A magnitude 4, 1 producing a 4. 5 at aftershock is backwards from how stress release typically works. Something else is happening. Something is loading stress into these patches faster than a single rupture would normally produce. If the Bartlett Springs Fault has never produced a large earthquake in the historical record, it is fair to ask why anyone should be nervous about it. The answer matters because of what happened 6 weeks before. On June 24th at around 7:45 in the morning, a magnitude 5. 6 struck Redwood Valley about 9 miles north of Ukiah. It cracked structures. It caved in roofs. At the peak of the outage, 10,000 Pacific Gas and Electric customers lost power, and the Mendocino County office reported injuries, though no deaths. A research scientist at UC Berkeley called it the largest earthquake on the Makama Fault in 75 years. Here is why that event is the load-bearing counterexample to every reassurance about creeping faults. The Makama Fault creeps, not theoretically, not by inference from rock chemistry, measurably. Alignment arrays put surface creep at more than 4 millimeters per year near Ukiah and Willits. It is the neighboring branch of the same regional system, running about 110 miles from Healdsburg up to Laytonville. It is an extension of the Hayward Fault system. It is a documented, instrumented, actively creeping fault. And in June, it produced an earthquake that damaged buildings and injured people. Creep does not mean safety. At most, it means the maximum plausible event may be smaller than the fault's raw length would suggest, and even that is contested. The geosphere authors say so directly. The role of fault creep in reducing the magnitude of large earthquakes is, in their words, the subject of debate. So the sentence, the Bartlett Springs Fault creeps, therefore it is fine, is not a conclusion anyone is entitled to. The fault next door creeps, and it hurt people in June. Line up the last 6 weeks and the pattern gets harder to wave off. June 24th, the 5. 6 on the Makama near Ukiah. July 10th, a magnitude 4. 1 on the Bartlett Springs Trace. July 28th, a 4. 3 on the Makama near Cloverdale, inside a sequence that kept producing events into early August, and now Tuesday and Wednesday, the Bartlett Springs cluster. 3 distinct segments of one regional fault system active in turn over 6 weeks. None of that establishes a causal chain. Faults 40 miles apart do not straightforwardly trigger each other, and static stress transfer falls off roughly as the inverse cube of distance, which kills that idea fast. But what it establishes is that the Coast Ranges system north of the bay is doing more than its baseline right now. The system is active. The system is responsive. Scott Dam sits nearly on top of the Bartlett Springs Fault Zone. It impounds Lake Pillsbury, and it is one of 2 dams in Pacific Gas and Electric's Potter Valley project. The other is Cape Horn Dam downstream. A utility built a concrete structure holding back a reservoir almost directly above a fault line that some models say can produce a magnitude 7, so the utility needed to know what that fault could do. The 1986 trench study, the one that found 3 prehistoric ruptures and gave us the only long-term record this fault has, was not a curiosity-driven research project. It was a final report by geometrics consultants commissioned by Pacific Gas and Electric. Its formal title describes a geological assessment of the seismic potential of the Bartlett Springs shear zone for Scott Dam. The 2024 serpentinite study was likewise supported in part by the same company. Every significant thing we know about the danger of this fault, we know because something valuable was built on it. The utility's behavior suggests it takes the answer seriously. Pacific Gas and Electric has lowered the reservoir level at Lake Pillsbury in recent years, specifically to reduce loading. Not a press release. A physical action with a real operational cost taken because the operator treats the seismic risk as concrete rather than theoretical. The company has also filed a surrender application and decommissioning plan with federal regulators moving toward eventual removal of both dams. The stated primary reason is economic. Seismic issues have also been cited, and Lake County officials have publicly challenged that reasoning. This brings us to the theory circulating online, and it deserves a straight answer rather than a dismissal because its factual core is unusually solid. The claim is that the dam is coming out because somebody knows the fault is about to go. The pieces are real. The reservoir was lowered. Seismic issues were cited. The dam is being decommissioned. But federal surrender proceedings run for years through a regulatory process. They are not an emergency response to a specific imminent earthquake. And no such earthquake has been forecast by anyone. The Federal Energy Regulatory Commission issued scoping documents in May 2026. The surrender application and decommissioning plan are moving through the normal FERC timeline. Dismantling could begin as soon as 2028 if approvals move forward. The truth underneath the theory is more interesting than the theory. This hazard was never a secret. It is documented in reports a utility paid for and summarized by seismologists who use the phrase potentially dangerous in public. The same answer applies to the broader suspicion that somebody is sitting on bad news here. The most alarming assessments of this fault are the published ones. What is actually true is narrower and in its way worse. This fault is understudied not because anyone suppressed the work, but because it runs through steep, remote, heavily forested terrain where almost nobody lives, and hazard research funding follows population and infrastructure. The honest version of the suspicion is not that they are hiding it. It is that nobody was looking because nobody lives there. The academic interest follows the human exposure. The funding follows the risk to people. The Bartlett Springs Fault has neither in abundance north of Round Valley. Start with the base rate because it is the most likely outcome by a wide margin. Globally, the fraction of moderate earthquakes followed within days by a substantially larger event on the same structure is a few percent. A magnitude warranted 4. 5 is overwhelmingly likely to be the largest event of its sequence. The energy released in this cluster is trivial against the fault's capacity. The 4. 5 alone is about 16,000th of a magnitude 7. Nothing this week relieved any meaningful strain. Whatever is loaded, there is still loaded. The specific thing to watch is location, not magnitude. The July 10th event struck about 18 miles along strike from this week's cluster. If a third cluster appears further northwest toward the northern end of Round Valley and the transition below the Mendocino Triple Junction, where the San Andreas system hands off to the Cascadia subduction zone, that is genuine long strike migration on a section of fault whose behavior is unmapped, and it would change how this sequence reads. If the activity fades in place over the coming days, it was a stuck patch letting go and nothing more. The second thing to watch is whether anyone extends the mapping. The 2024 study drew a hard northern boundary at Round Valley and said so in writing. The ground that just produced 3 magnitude 4 class earthquakes lies at or beyond that line. Whether the aeromagnetic modeling gets carried north into that gap and what it finds when it does is the single measurement that would most change the hazard picture here. Right now, the honest position on the northern Bartlett Springs Fault is not that it is dangerous or that it is safe. It is that nobody has looked. If the northern section behaves like the locked model predicts, we have a fault segment capable of surprise. If it behaves like the creeping model predicts, we have a fault that talks to us through frequent small events. We cannot know which until someone flies the northern profiles and does the work. That is not hypothetical. That is a specific, doable study that would answer the question. It has simply not been funded. The third thing runs on a longer clock. If the decommissioning completes and the dams come out, the legal obligation that drove almost all of the research on this fault goes with them. When the dam is gone, so is the reason anyone was required to care. What we are left with is a fault at least 120 kilometers long, running from north of Round Valley down through Clear Lake and onward toward the Eastern Bay Area. A dam sitting nearly on top of it with its reservoir deliberately lowered. 3 prehistoric earthquakes recorded in a trench, the most recent within the last 1,000 years. A slip rate nobody can pin down within a factor of 9. And on Wednesday afternoon, 2 earthquakes, 59 seconds apart, less than 3 miles below the surface in the one section of this fault that the newest and best science does not cover. We will know more if the sequence migrates northwest, and we will know more if somebody flies the northern profiles. Until one of those happens, the accurate statement about the Bartlett Springs Fault is the uncomfortable one. This is a structure that has broken at magnitude 7 at least 3 times, in a place where the measurements that would tell us whether it is about to do it again have never been made. The nervousness is not misplaced. It is just honest.